All right, so the Ostwald process. This is from page 123, number 126. Wait a minute, that's Oswald. Wrong one. Ostwald process. This process is not a Disney process. It's a process used to make nitric acid. Now, nitric acid is a very corrosive acid. It reacts very, very well, very, very badly, depending on what your point of view is. But it's used to make pharmaceuticals, used to make explosives, things like TNT is made from nitric acid. Pharmaceuticals are made from nitric acid. Nitroglycerin, which can be an explosive, can also be heart medication, is made from nitric acid. A lot of different things. Now, this process itself was first patented in order to make fertilizers. So things like you put on the ground or put on your plants to help them grow. That's what this process is first patented for. All right, so in order to answer this question, we're going to take our same steps. First one is read and understand the background information. Next up, we're going to identify the question. Then write out our given information. Write out and balance our chemical reaction. Now, they give us a chemical reaction here. It's actually a mechanism, so it's 3 different chemical reactions that are carried out in process. But those are already balanced, which is kind of too bad, but that is what it is. So we don't actually have to do that. And last step is going to be to use our stoichiometry. So let's do it. Alrighty then, to understand the background information, they give you this. Nitric acid is produced commercially by the Ostwald process, represented by the following equation. So nitric acid, that's HNO3, so hydrogen nitrate, but it's an acid, that means that it is an aqueous solution, or it's in water. So it's hydrogen nitrate in water. It's produced commercially, so commercially that means on a grand scale. We talked before about this, that nitric acid is used to make all kinds of things, from explosives to pharmaceuticals, to a whole bunch of different other reactions that it can be used for. It can also be used for metal etching and just plain eating away metal. And the Ostwald process, that's named after the person who patented it. So this is a 3-step reaction here. So you've got your first reaction. The products from the first reaction are fed into the second reaction. The products from the second reaction are fed into the third reaction. So let's look at those reactions. The first one, you're taking ammonia. That is your starting reactant. And you're burning it in the presence of oxygen to make nitrogen monoxide and water. Now, this nitrogen monoxide is really what you're interested in, because that's what you're going to be feeding into the next part of the reaction. Water will go into the third reaction, actually, so you can concentrate this down. We'll talk about that in a minute. But nitrogen monoxide is then fed into the second reaction here. Now, it is also burned in the presence of more oxygen to make nitrogen dioxide. So you're oxidizing this ammonia, then further oxidizing it into nitrogen dioxide. Now, this nitrogen dioxide then is fed into the third reaction along with the water that you produced earlier. So this uses all of your products, which is why it's a very, very good mechanism for doing this. You have very little waste here. So you take nitrogen dioxide, combine it with liquid water, and that makes your nitric acid. Now, you do have a byproduct of nitrogen monoxide, which is usually fed back into this reaction to make more nitrogen dioxide to produce this. Now, we are not going to concentrate on this time, though, the nitrogen monoxide. We're just going to be concentrating on the nitric acid. But it's a very good reaction for making lots and lots of nitric acid. And this nitric acid then can be shipped to all corners of the globe to make, again, fertilizers, pharmaceuticals, weaponry, all kinds of things like that. All right, so to identify the question, what mass of ammonia must be used to produce 1.0 times 10 to the 6 kilograms of nitric acid by the Ostwald process? All right, so that's kilograms of hydrogen nitrate by the Ostwald process. Assume 100% yield in each reaction. All right, so the mass of ammonia, that's what we're trying to identify. So what is the mass of ammonia? What does that mean? Mass is either grams or kilograms of ammonia. So that is going to be our final answer should be in these units, either grams or kilograms. And we're probably going to end up in kilograms because we're starting with kilograms of hydrogen nitrate. So we're going to be going all the way to kilograms here. Okay, so for our given information, again, same paragraph here. Our first thing that we have is 1.0 times 10 to the 6 kilograms of hydrogen nitrate. That's how much we need to make. That's pure hydrogen nitrate, not nitric acid. If it was nitric acid, they would have put the parentheses AQ behind this. But this is 1.0 times 10 to the 6 kilograms of pure hydrogen nitrate. So that's one piece of given information. The next piece is assume 100% yield. So what does that mean? That means that your actual equals your theoretical. So this is not in real life, although this process comes very, very close because of how well each product is used in the next reaction. So your actual equals theoretical. That means you lose nothing to your experimental process, to real world processes that would normally take away from this. So your actual equals your theoretical. That's why they tell you 100% yield. Now, you're also assuming that the nitrogen monoxide produced in the third step is not recycled. So we'll take a look at that once we look back at the mechanism. So our plan for this. Given our mechanism again, there we go. So we start with ammonia and we end in hydrogen nitrate. So in order to do this, ammonia is made into nitrogen monoxide. Next, that nitrogen monoxide is fed into the second reaction. And this nitrogen monoxide is added to more oxygen to make nitrogen dioxide. That nitrogen dioxide is fed into the next reaction. That nitrogen dioxide then is combined with water to make hydrogen nitrate. Okay, so we start here with how much hydrogen nitrate that we need. So in order to figure out how much ammonia we need to use in order to produce that much hydrogen nitrate, that was 1 times 10 to the 6 kilograms of this, we'll have to work backwards. So in order to make 1 times 10 to the 6 kilograms of hydrogen nitrate, we need to first figure out how much nitrogen dioxide is used to make that. Now that nitrogen dioxide comes from this second reaction. So from that amount of nitrogen dioxide, we can figure out how much nitrogen monoxide is needed to make that. Now that nitrogen monoxide comes from this first reaction, and from the amount of nitrogen monoxide, we can figure out how much ammonia is needed to make that much nitrogen monoxide. So we're going to have to go backwards here, backwards along these arrows. Alright, so let's go ahead and do it. So I'm giving you the mechanism up here for reference. Hopefully you're taking notes during this video, so you have this already written down on your paper. Hopefully you tried it already on your own, which would be even better. But this mechanism here is for reference to keep us on the right track, to make sure we're going in the right direction. We're going to start with our 1.0 times 10 to the 6 kilograms of hydrogen nitrate. That's how much we need to make, so we're going to go backwards. Now in order to go backwards, again, our plan is to go from hydrogen nitrate into nitrogen dioxide. From nitrogen dioxide, we're going to go to nitrogen monoxide. From nitrogen monoxide, we're going to go to ammonia. Now, in order to convert from one molecule to another, though, we know that we need a molar ratio. In order to have a molar ratio, we need our unit to be in moles first. So, converting from kilograms into moles, we don't have a specific conversion for that. So, we're going to first convert from kilograms into grams. So, 1,000 grams per kilogram. So that gives us the amount of grams of hydrogen nitrate. And from there, we can convert to moles using the molar mass, which of course we get from the periodic table. So at molar mass, that's 3 oxygen, so 16 times 3, 32, 48, plus another 14, plus another 1.01. So 63.02 grams of hydrogen nitrate per 1 mole. If we stopped right here, this would tell us how many moles of hydrogen nitrate we need to produce. But that's not what they asked for, so we're going to keep on going. Now that we have it in moles, though, we can use our molar ratio. So for every 3 moles of nitrogen dioxide, we make 2 moles of hydrogen nitrate. That comes from this third reaction here. If we stop right here, this tells us how much nitrogen dioxide, how many moles of nitrogen dioxide it takes to make 1.0 times 10 to the 6th kilograms of hydrogen nitrate. But that's not what we need. And we do know, though, that all of this nitrogen dioxide comes from this second reaction. So we can continue to trace it back. Run out of room here. We're going to go on to the next line. But we have our moles of nitrogen dioxide, which is how much it takes to make hydrogen nitrate, but it's also how much comes out of this second reaction. So using this second reaction, we get our next molar ratio, which is a 2 to 2 molar ratio. For every 2 moles of nitrogen dioxide that we make in that second reaction, we started out with 2 moles of nitrogen monoxide. So this is the amount of nitrogen monoxide it takes to make 1.0 times 10 to the 6 kilograms of hydrogen nitrate. We can't stop there. This amount of nitrogen monoxide in moles that we've calculated is also the amount of nitrogen monoxide that comes from this first reaction. So that's where our next molar ratio comes from. We know how many moles of nitrogen monoxide we have. We're going to use that first reaction to get our next molar ratio, which is a 4 to 4 mole ratio. So 4 moles of ammonia is needed to produce 4 moles of nitrogen monoxide. Now they asked us for a mass, so this is the amount of moles of ammonia it takes to produce 1.0 times 10 to the 6 kilograms of hydrogen nitrate. We don't need it in moles, though. We need it in a mass. So we can go from moles to mass or moles to grams using our molar mass. So 1 nitrogen is 14.01, 3 hydrogens are 1.01 each, so that's 17.04 grams per 1 mole of ammonia. And in order to make this number more manageable, you've got kilograms here. So we're going to convert this into kilograms. So 1,000 grams per kilogram, or 1 kilogram per 1,000 grams. There we go. Now all we need to do is plug this into our calculator. So saving ourselves a couple of keystrokes here. The 1,000 on top and the 1,000 on bottom here, those cancel. 2 on top, 2 on bottom, those cancel. 4 on top, 4 on bottom, those cancel. We have our units all canceling and lined up. Kilograms of hydrogen nitrate, grams of hydrogen nitrate, moles of hydrogen nitrate, moles of nitrogen dioxide, moles of nitrogen monoxide, moles of ammonia, grams of ammonia. We're left at kilograms of ammonia. So in order to plug this into your calculator, it's just 1.0 times 10 to the 6th. Again, this one and this cancel. Divided by 63.02 times 3 divided by 2. These two cancel. These two cancel. Times 17.04. And your final answer is 4.1 times 10 to the 5th kilograms of ammonia. There we go. There's the final answer, kids. It takes 4.1 times 10 to the 5th kilograms of ammonia. You need to feed into this process. It goes through these 3 reactions and produces 1.0 times 10 to the 6th kilograms of hydrogen nitrate.